Okay. Can everyone hear me okay? Okay, awesome. So, hi everyone, I'm Suchi, and I am going to be a third-year PhD student at the University of Hawaii at the Institute for Astronomy. And my favorite topic and what I research is the chemistry of planet formation. So, I wanted to do kind of a broad talk in how basically the early chemistry of a disk and when a star forms, eventually, like it's from the very beginning that dictates whether life can eventually form with the resulting planets. So it's like the very early disk chemistry determines a lot of things. So I kind of wanted to highlight the whole process from like early disk dynamics and what happens and how we can piece that together eventually through our solar system as well. And I don't think any talk like this can start without this quote, which is my favorite. And it's kind of what got me into studying chemistry and astrochem specifically. It all begins with like, how did we come to be? So the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies are made in the interiors of collapsing stars. We are made of star stuff. So that's my favorite quote, and I think perhaps it's one of the most of ours, you know? So I think it sets the tone for what kind of talk this will be. And I think the motivating question for astrochem and astrobio is how did life come to be? And before we get into the science, I kind of wanted to illustrate the history of our origin of life theories. I don't know if any of you have any background in chemistry or bio, but my degree in undergrad was actually chemical and biomolecular engineering. So that coupled with astrophysics, so my whole, maybe these are some topics that, you know, a regular physics background did not touch on, so I kind of wanted to show and highlight how our understanding of life has changed dramatically over the last few hundred years. So pre-1800s, we thought that organic matter was biogenic, so it could only be formed by living organisms. And we thought that it means, like our definition was, organic contains a carbon and a hydrogen bond, and it could only be formed by other living organisms. And then in the early 1800s, we figured out that we can synthesize amino acids from inorganic material in the lab. And as we know, amino acids are the building blocks of life, and the holy grail of astrochemistry and astrobiology is detecting glycine, which is the simplest amino acid. So amino acids ended up being really important because we figured out that in our kind of limited understanding of life, these molecules could be formed from non-living matter. And then in the 1940s, so we're skipping a bunch, and we first detected organics outside of the solar system, which was a major discovery, and I'll explain why in a few slides. And then in the 1953, there was the classic origin of life experiment. I don't know if some of you have heard of it. It's the Miller-Urey experiment, where amino acids were formed from hydrogen, water, methane, and ammonia. And so I kind of wanted to illustrate what the Miller-Urey experiment was. So these four molecules were in the liquid phase, and they were going to resemble Earth's early ocean, and they were heated up to induce cloud formation to form something like Earth's primordial atmosphere. And then there were electrical sparks that mimicked lightning, and then it was condensed, and this was a closed cycle, and we let enough time go by, and we saw that amino acids could form. And the really cool thing is, in 2008, these 1953 vials were reanalyzed. And so in 1953, there were 5 amino acids that were formed, glycine being one of them. And after whatever 50 plus years, we ended up finding over 100 amino acids. So enough time had passed by that even more than what we need for life could have been formed. So this is a 2008 discovery that with the same vials, like time ended up being really important, but even on a time scale of human life, we could form even more, like an order of magnitude more amino acids than the initial discovery. So this was a pretty remarkable origin of life experiment. And so the way that this talk, I wanted to organize it is first introduce astrochemistry and molecules, and complex molecules, and then highlight what kind of formation pathways exist to create these molecules, then kind of go through planet formation and how we can currently study the solar system to inform our theories of planet formation. So the questions that for astrochemistry is, why was detecting organics in the ISM surprising? What's the cosmic chemistry cycle and the current chemical inventory? So detecting CH was really significant because before this, we thought that the interstellar conditions were too harsh to form these molecules. So some of the reasons are we have low temperatures, nearly zero pressure, and intense radiation. So I don't know, I kind of wanted to make it interactive. So why would these be too harsh to form molecules in the ISM? If you don't have answers, that's okay. I had presented this to my AP Chem class, high school AP Chem class a couple weeks ago, so kind of modeling off of that. But if it's low temperatures, you can't overcome activation barriers. Nearly zero pressure means that you're decreasing the collisional frequency, so you can't, your reaction rate is reduced, and then intense radiation destroys molecules. So our early understanding of chemistry basically led us to believe that we couldn't form these molecules. So CH, the simplest organic molecule that we know, detecting it in the 1940s, opened up astrochemistry. So this was around 1968 is what we believe to be the start of astrochem. And I kind of wanted to illustrate the definition because this is how chemical species form and react in the ISM. But something closely linked is cosmochemistry, which is specifically how did the elements get distributed right from the early Big Bang, and how that distribution affected our current understanding of solar system formation. So even though cosmochemistry and astrochemistry seem to be really similar, they kind of branch out in the sense that cosmochemistry deals a lot with like radioactive elements and how we date and stuff. So it's a very interdisciplinary science, and you'll see that we need understanding of geology and chemistry and physics and astro to basically answer this question, which is what made Earth perfect for life. And so the cosmic chemistry cycle, I'm sure many of us know this. So you have cold regions in interstellar space, so you have molecular clouds that then undergo gravitational collapse to form a protoplanetary disk where stars and planets begin to form. And something I think a couple of years ago was that we thought that stars formed first and then the planets, but we now see that even in the early stages, so class 0 disks, planets are beginning to form at that same time. So it's kind of it's very intimately linked. And then we have our stellar systems that form, and then you have your stellar death, and then you return those elements back. And so based on the chemistry that we see of our solar system, we would have had to undergo several generations of these stellar deaths to be able to form the complex chemistry that we have now. And so that kind of, I think that's something that kind of illustrates how special we are in terms of that so much had to have happened for us to even have the perfect chemical ratios for the solar system to form. So one of the most important chemical ratios that we look for in protoplanetary disks is the carbon to oxygen ratio. So for us, I think that's 0.6. But if we had it greater than 1, we would have a very different environment that would have been filled with like carbides, and all these early ratios can basically dictate how planets are differentiated when they're forming. So what elements want to go into the core versus the mantle, and all of those play really important roles. So this cycle and how elements are redistributed matters a lot in terms of what eventual planets can form. So in the ISM, we have, this is from September 2021, so I think like at least like 5 or 6 more have been detected since, and these are just 2 to 7 atoms. there's up to 60 atoms that we have detected. So there's 241 so far as of September 2021. And here I've highlighted some of the common prebiotic ones. So those are the ones that we think are the building blocks for molecules that are essential to life. And then I highlight the Miller-Urey molecules. So it's impressive that we have detected everything in space already that we have found in the lab experiment to have formed amino acids. So we still have yet to have real convincing detections of glycine. There have been some papers that say they have, but the whole thing is, the whole goal of astrobiology is to see if we will be able to detect that. And something that's interesting in terms of the molecules that, yeah?
So when you say ISM here, so what, like, ISM could be like between stars or just in a solar system. So what are we exactly talking about here?
Wait, say that again?
So where were these molecules detected exactly?
So in our galaxy.
In our own.
Yeah.
Okay.
So these are basically, most of them are in nearby star-forming regions. So Orion, Perseus, Serpens, Ophiuchus. So the common star-forming regions. A lot of the rich chemistry happens in the Orion hot core. So these are basically in like the cold, dense molecular clouds nearby our galaxy.
So it's mostly found in cold molecular clouds, not some hot ISMs or H2 regions, right?
Yeah, so we're gonna get to that, which is, yeah, so that's a really good point. They are formed in really cold regions, and so there's a huge shift on our perception, which is where we get to here. So 99% of the ISM is in the gas phase, and solids make up 1% of the ISM. But what we found is that gas phase reactions cannot reproduce the observed abundances. So in like the last 10, 15, 20 years, we found that ice reactions are really important. But we found 241 molecules in the gas phase and literally only 10 molecules in the ice phase. So these are, you have carbon monoxide, water, OCS, CO2, OCN, ammonia, formaldehyde, H2, CO2, and then CH4, so methane and methanol. And one thing of note is that there's only one sulfur-bearing molecule, so OCS. So I'm about to propose my thesis at the end of December, and it's a focus on sulfur chemistry because sulfur is really important in terms of in terms of molecules that are essential to life. So if we remember CHO, N, P, and S, so phosphorus and sulfur are important in lesser amounts, but they're still important, and we don't really have any solid phase sulfur experiment, so we have no formation pathway that can confirm how OCS forms or any sulfur-bearing molecule, which is important in terms of prebiotic chemistry. But I think the main thing to take out of this is that most of our reactions happen in ices, but only 10 have been detected. So hopefully JWST and future improvements to our detection abilities will kind of expand this list. So this is kind of a big, because there were so little that were formed in the ice phase, we really didn't think that ices were important. And especially, like, let's go back to why we thought molecules couldn't be formed in the ISM, like low temperatures, you can't overcome activation barriers. So how come ices are where complex molecules are formed? So this was a major shift in our understanding in how complex molecules are formed. So we'll go, that like segues perfectly into formation pathways. So how do we study these? A little review on molecular transitions and the different gas and solid phase pathways. And so as we know, molecules are detected through spectra. And so this is just an example of in the Orion Nebula, like how rich the chemistry is there in all of these different lines. And I kind of wanted to highlight how ALMA has really changed our understanding. So there are 3 large programs, so there's another 4th one, but these are the 3 that have happened or are happening. So I'm part of the EDISC large program, which is early planet formation and metadisks, but I kind of wanted to highlight the history. So large programs are basically these really like big endeavors that use most of ALMA to basically piece together a really a really important topic that needs like a lot of data to basically say something significant. So like D#, for example, it looked at class 2 disks, which are slightly more evolved, and it was the first time that we saw how ubiquitous structures could be. And you can see the diversity of structures that were found. So this was a very pivotal mission, which basically showed that there's so many different ways these disks can arise and these disks can form, and very different planets will form from each one because the spirals, the gaps, what material, the size of it, all of that will affect what chemistry can occur. And then last year, Karin's group did molecules at planet forming scale, so the MAPS program, and that focused on 5 disks, but really deep understanding of the chemistry of them. And so based on her work, like I'm gonna go to her lab in January to work on the sulfur aspect. So this is basically the mission that told us most about like revealed our gaps in the chemical understanding. And then, as I said earlier, we didn't think that we thought planets formed at this stage, so where these structures are beginning to exist. But, and we think that these structures are a result of planet formation, what's happening within those disks. For example, the gaps could be because like a Jupiter-sized planet is blocking dust migration. So we thought that this is where planets are forming. But recent discoveries show that it can be at earlier stages. So the E-disk is comparable to the D# mission, but for class 0 and 1. And we're trying to figure out if there's something we can say, like in terms of population statistics, like what is common or not common with class 0, and how like basically kind of focusing on the missing link between like the ISM, the diffuse ISM, and then class 2 disks, like what is happening in that chemical-wise or chemistry-wise or dynamics-wise. So these are kind of the revolutionary programs that ALMA has allowed for us to do and will inform like future JWST observations. And so this is just an example of how the telescope, like how rich we can see in terms of radio astronomy. So this is just a pretty picture. I think I showed it to the high school AP Chem class, and I think it's one of my favorite ways to visualize like why radio waves are really important and how radio astronomy has really changed the game in terms of astrochemistry. And so molecular transitions, a lot of us probably remember like when an electron gets excited and emits a photon, after it goes back to the ground state. But the two other ones, so this is from optical, but the two other ones are rotational. So the reason that we need microwave or radio, or we need to have a multi-wavelength understanding, is that some molecules can only emit in different wavelengths. So rotational is when you have a molecule that has a dipole moment, so a clear difference. So here, it's just to show there are 2 different atoms, and if they rotate, the way they rotate will actually affect what spectra we see. So rotational diagrams can tell us what molecule we're seeing because of the difference in the element and how they're moving. And then vibrational, so if you have elements that are either locked, so in ices, or they're of the same element, basically their bond can have different vibrational modes. This is why infrared detections are important for ices, and why JWST will have a lot of cool discoveries in the upcoming months and years. Oops, sorry. So basically, there's 2 different ways of gas phase reactions and surface chemistry, and we think that the most likely ways that these molecules can form are through bimolecular reactions, so two molecules or atoms at a time. So that means that to form complex molecules, you need to have a series of these to happen. And the reason is that three-body collisions or anything greater, you need really precise like geometric orientation of the molecules. So depending on, so this is called like stereochemistry and organic chem, if you've heard of this, but basically if the orientation isn't precise, the reaction can't occur. And in the diffuse ISM, like where these molecules are located, there's not enough pressure to have enough collisions. So in terms of probability, like you're not going to have three-body collisions. So that's why surface chemistry and ice reactions are thought to be where these complex molecules can form, because these neighboring atoms, if they're excited by cosmic rays or something, they can move. They're close enough and it's dense enough to have these reactions occur. But I wanted to highlight some of the gas phase processes. So an ion-neutral reaction is you have an ionized and a neutral atom. You have neutral-neutral. You have photon emission, and then you have dissociative. So these are the gas phase processes, and these are what we focused on for the early part of Astrochem. But as you said, these reactions these models did not match our observed abundances. So the way these are formed through surface chemistry is that there are, it happens on like dust grains or ice grain mantles, and so how do gas species absorb onto the grains? How do they migrate when they're on the surface, and how do they desorb? And so the ways that these commonly happen are atom addition reactions, so hydrogenation, like let's say CO, which is the second most abundant molecule, and a tracer for H2, which is the most abundant molecule. You can keep adding hydrogen, so you can get formaldehyde, so H2CO, and then you can get methanol, and methanol, with respect to water, is one of the most common ice molecules, so we know that hydrogenation reactions are very, very likely on surfaces. And then there are two mechanisms that maybe you haven't heard of. They're called Langmuir-Hinshelwood and Elie-Rideal mechanisms. So in Langmuir-Hinshelwood, you have two molecules that are in the gas phase, and they absorb, and then they react. But in Elie-Rideal, you have one in the gas phase, one already on the surface, and then they react. So these are just different surface reactions that you monitor, and these mechanisms are what you characterize when you have ice experiments. And generally, the rate limiting step for these is the diffusion. So how do these gas phase species absorb onto the grain? And then in terms of planet formation, I just wanted to highlight what are the disks, how do they form, and why does location matter? So there are three or four different stages that we have. So class 0, 1, 2, and 3. So and the 0, you basically have the envelope, and this envelope basically fuels accretion. So this is where your protostar is still forming, and you have an accretion onto the star, and you have, in terms of what temperatures we're looking at, you have an inner envelope that's about greater than 100K. So there's like this common misconception in a lot of Astrochem papers where they say like as you move closer to the star, your molecules are evaporating, but this gradient happens so fast they're not evaporating, they're sublimating. So they're going directly from the solid phase to the gas phase. And this is the hot core, so I don't know if you've heard of like little hot corinos or hot cores. So the chemistry in these regions are very different from what you would see outside. And in a few slides we'll show which molecules trace which parts of the disk. And so also as you're having, as your protostar is accreting, they have to get rid of the excess angular momentum, and that's through jets. So we can see these outflows in a lot of our sources in the E-disk. And so you have molecular jets, which are really, really fast, and then you have low velocity that are outside of the outflow. And so different molecules can form in these because there's very different temperatures and dynamics happening. So it's in these fast regions that there is a lot of those like 60 atom molecules that we form, because these are where the density is high enough to induce these reactions. And then you have these things with the star disk boundary layer, so there's a lot of fluid dynamics that happens when these two are meeting. And so here you have intense UV chemistry, which is very different than what we see in like ice chemistry, for example. So these are like similar to photon-dominated regions that some of you might be familiar with. And then when you get to class 1, it's a natural outcome of rotating and collapsing cores. And at these early stages, so 0 to 1, it's very hard to distinguish what is the envelope and what is the disk. And so when we do study a bunch of these disks and we see what in more evolved or early ones, we can kind of see which molecules exist to kind of separate the masses, because there's very different things happening if it's like accreting onto the stellar core or whether it's in the disk where planets form. So it's very difficult, and that's what eDisk kind of seeks to understand. It's like a lot of issues that we're having is doing with separation between the envelope and the disk, and those result in very different molecules that can form. And so as you know, location matters, and as you move outward, you're able to condense more molecules onto grains and different ones, and so that's what creates our snow lines. So you have rocks and metals, your water ice, your nitrogen, sulfur, carbon dioxide ice. So as you move outwards, there is a lot more chemistry that can happen. So when we do see volatiles that formed Earth or these complex molecules, we know that there has to have been some sort of dust or ice migration inwards. And so our early understanding was that planets formed exactly where they are, so we call that in situ formation. But as we find more planetary systems, we realize that our solar system is more of the exception rather than the norm. So every time we think we know something about planet formation, we find a new system and it completely obliterates our understanding. And so a lot of things that we seek to understand is how chemistry can occur outwards, and then what happens as it comes in and is sublimated, and what reactions can occur. So these snow lines are really important, and they're a natural consequence of temperature decreasing and condensing of different elements. And so this is kind of a summary of that paper. So you can see that after studying several disks at different stages, we kind of have a good understanding of what molecules can be found in what part, and these can be used to kind of distinguish what phase a protoplanetary disk is in, and what elements or what molecules are available for planet formation. So we can see that some of these are very different. And isotopes, so isotopologs, so 12CO versus 13CO versus C18O, all of those can happen in very different locations. So you can trace isotopes, and we'll see later on why isotopes are really important. But distinguishing that it's not just the molecule itself, it's also its isotopes that end up being really important. And our kind of final session is how do we use these principles from early chemistry and astrochemistry, so the interstellar medium, how do we go into cosmochemistry and how our solar system formed? And something that's really cool is like what actual sample returns, so meteorites are going to another planet, what can it tell us, and what's the future? So as we know that we have the inner rocky terrestrial planets and our outer gas and ice giants, and initially we thought, oh, this is just because of temperature, like, cold planets, or the icy planets were outwards, and the rocky planets, like the difference in them was basically because where they formed, so the in situ formation. But recent planet formation models show that if Jupiter did not form as fast as it did, our inner planets would look very, very different. So I think we just hit over 5,000 exoplanets detected, like in May. And the most common planet that we see, and it might be due to observation, it's likely due to observation bias, but it's something that we don't have an analog of in our own solar system, which is hot Jupiter, so really big planets that are really close into the star. So we don't have that, and so we think that basically looking at other planets in our solar system can inform what happened to Earth specifically and what makes a habitable planet. So our solar system basically provides the best playground and the only one where we can actually get physical samples from. So one of the things is what's the difference between inner and outer planet formation. And so the way that we piece this together is actually studying meteorites and their composition. So in the lab, this is where cosmochemistry comes into play. And what we found is this thing called the isotopic dichotomy. And we found that the inner planets are non-carbonaceous and the outer gas and ice giants are carbonaceous. So there are these two classes of meteorites. And we're able to see this dichotomy in both achondritic and chondritic meteorites. So what that means is that chondritics are the ones that we think are pristine and they haven't been processed and they're what made the sun. So they're directly from the solar disk that actually formed our solar system. And then achondrites were processed, so whether they were subjected to, if they were impacted or if they were melted and re-solidified, like these are basically processed. And so the fact that we see this carbonaceous and non-carbonaceous dichotomy with both pristine and processed meteorites gave us a huge clue, and this is kind of a recent discovery to understand how our solar system formed. And so this is kind of just a summary, but more technical. So the fact that we see it in both of the reservoirs, and we see it not just for a couple isotopes, but several isotopes. So we see it for oxygen, chromium, titanium, molybdenum. So a bunch of different molecules show this dichotomy. It basically tells us that there is a lot of migration. It basically was like a +1 for dust migration models. And so one of the major things is we're going to get our sample return from Mars soon, and there are missions to go to Venus and Mercury. And so in one of my meteorites classes, we actually did we actually wrote a proposal for a Mercury sample return and motivating it. And the biggest motivation for this is basically if we can find that those samples also show this dichotomy, it shows this kind of, it would really help us understand how our solar system formed. So there's actually a lot of importance to lab work and understanding, like in the lab setting, how can we analyze these rocks. And that has to link to astrochemistry. So it's like a very interdisciplinary field, and if we go, it all started, as I said, from the early disk chemistry. So it's kind of cool that through these rocks and through, we can piece together what the early solar system was like. And so this is kind of the isotopic dichotomy. So you can see that this is for different isotopes. So you have titanium to chromium, oxygen to chromium, molybdenum to nickel. And you can see that there's this kind of two different reservoirs for the inner planets and the outer planets, so the carbonaceous and non-carbonaceous. And you can see that Earth, Mars, and Moon, that we have been able to detect or measure those rocks. We can see that it falls directly into the non-carbonaceous reservoir. So this is actually a recent paper, so in 2020. So this is kind of like the biggest question right now in terms of cosmochemistry, and kind of motivates future sample return missions for the interterrestrial planets. And something that's really important that I also think is, it's one of my favorite questions, and it's the Venus and Earth bifurcation. So these planets, as you know, probably Venus is our evil twin. One rains sulfuric acid and the other harbors life. And so astrophysically speaking, they were formed from the same dust, but they have very different paths. And the only reason we understood our greenhouse gas effect was by studying Venus, where there's the runaway greenhouse gas effect. So understanding Venus and its atmosphere basically helps us inform in terms of climate change. And so there's no other planet out of the 5,000 plus planets that we've seen. There's no other planetary system where we see very similar planets as close in size as Venus and Earth are. So I'm really excited for the 2 Venus missions that were just given a go by NASA, so Da Vinci and Veritas, which are going to look at this atmosphere and the surface. And so this is a really pressing question in terms of our planetary formation models. Like, we don't know where this fork in the path occurred and what created these 2 very different environments, even though in terms of size and density and location they were really similar. And I think one of my favorite fun facts is, like, if we looked at our solar system the way we look at other exoplanetary systems, we would actually think that Venus is more habitable just by the very the really loose definition of where water can be in liquid form. So it kind of shows us how much atmospheres and how cores and stuff differentiated really matters, and hopefully with JWST, like, looking at atmospheres and how they form can also help us inform this bifurcation and how what made a Venus versus an Earth-like planet. And so another really cool field that has been enabled because of these missions is comparative planetology. And so this is one of my favorite images. So you have Venus, Earth, and Mars together, and you see these delta formations, and it kind of shows us that physics is universal, but they were formed in very different ways. So Venus is because of lava outflows, Earth is because of life, something we think is unique to just us, and then on Mars it's early water, like it was because of running water, but you can see that it was a long time ago because you have these impact craters. And so something that is only starting to be appreciated is comparative planetology because of all of the missions that are now, where we have like enough of a data set to basically make these meaningful comparisons across planets. And so basically, I think we have this one data point for life, which is Earth, but we have these 7 other data points for what didn't create life. So what didn't create life is just as important to answer this question as how Earth came to be. So I think there's merit in and of itself to study these other planets to inform how Earth came to be. And so just a little summary, you have 241 organics that as of September 2021 were formed, and the ones that are essential to life have been detected, so the ones that, for example, the miliary molecules were found. And then most of these are formed in the solid phase, so in ices or dust grains. So that was contrary to what we expected. We thought because the ISM was 99% gas, like most of these reactions should have happened in the gas phase, but that's not the case. So ice chemistry and dust grain chemistry actually plays a huge role. Position along a protoplanetary disk affects what material is available, and also depending on the dynamics of a protoplanetary disk, whether dust can migrate or it's stopped by the formation of a planet, all of these different factors can influence what the resulting stellar system will be. And studying meteorites and rock samples provide clues to how our solar system formed. And one of the biggest open questions right now is, do Venus and Mercury fall in this isotopic dichotomy that we only recently were able to understand because of the advancements in our technology in terms of sample return. And I think that the most important part about this is kind of appreciating that, like, our story and how we came to be started not just in the beginning of our solar system, but our universe, because we have to have this regeneration of stars to be able to form the ones that have the chemical complexity to allow our solar system to form. And so I think a lot of times, honestly, with the state of the world, like, it's really, you can get really existential and kind of feel really insignificant, because I feel insignificant all the time, like, studying all of these things. But I think we can turn it around and be like, we're so special because for us to even exist, so many things have had to have gone correctly. So I think that's been a recent shift in my mind, because I think that you know, problems like climate change and COVID have felt really big for us to tackle. But I think in terms of grounding yourself, it's kind of cool to see how the complex chemistry that formed us actually began at like the very beginning of the universe. So that's, I think, what I take away from Astrochem and Cosmochem, and open to questions. So hopefully that was interesting and good stuff. Thank you.
Anyone have any questions? I guess, so maybe you said a little bit of this already, but in terms of laboratory chemistry, can you give us a little taste for what kind of questions you can answer in a lab, or
Yeah, of course.
what's like?
So basically, the most important things, maybe there's like this thing that I can show. I have this little thing, and it's basically something that I kind of show. As we are, so actually in the decadal survey, like that was just released last year, laboratory experiments were like considered very, very high priority, and that's because we're not reaching the realm, we're not data limited anymore, we're kind of physical understanding limited. So right now, a lot of our reaction models, they're basically extrapolations for like other old laboratory chemistry. For example, for sulfur, which I'm studying, it's kind of modeled after oxygen chemistry because sulfur and oxygen have the same reactivity because they're in the same period. And so those are just estimates. We don't really have anything that actually physically has been determined. So one of the most important things that we can get from laboratory experiments is like reaction kinetics, so rate constants, and how like absorption constants or desorption. So that kind of, those are critical parameters that we need for our reaction models that kind of model planetary formation. And so I think this is like a really cool link between the three major components, I guess, which is experiments, observations, and theory. And so kind of the observations are, let's start with that, like if you detect it, there's some way that it had to have been formed. So it kind of gives you the starting point for what your end molecule should be. So observations are important in providing that. And then you can have experiments that basically, okay, can this form? And so that's where the link between experiments and observations show. So observations give the end product of the, and motivates what experiments should happen. But in terms of our theoretical understanding to like piece together like a unified like planet formation theory, like observations kind of provide constraints for the modeling. So in terms of radial distance is a proxy for temperature. So can this reaction even occur at this distance, or did it have to migrate? So in terms of like understanding the temperature gradients in protoplanetary distance, that kind of gives limits for modeling. And then you can kind of, if you have experiments and observations, there has to, you can't predict that through a model that shows that you have some physics that's missing or chemistry understanding. So basically, you need all three parts to be able to piece together. So it's a very big undertaking, but there's a lot of cool places where you know, it shows that like the forefront of our understanding of planet formation requires a very interdisciplinary background. So I think that is why in the decadal survey there was like this huge emphasis on laboratory experiments, because you can't really predict something if you don't know physically if it can occur and stuff. And that's why I think it's really important for like chemists and astronomers to talk, because I've seen, I've been on the physical chemistry side, and they look at these proposals or stuff from astronomers, and astronomers are like, okay, these elements exist, like this plus that could equal that, but then you look at the chemists and they're like, that's physically not possible because like of stereochemistry or things like that. So there needs to be like kind of talk on both ends, because astronomers are really, astronomy is important because it's giving you the actual detections, but chemistry is important because physically can the reaction occur? Like there's a lot of do we know if other reactions will occur, or will oxygen chemistry kind of overpower sulfur chemistry? You know, like, there's a lot of different ways these paths, it's like very complex, and there's so many dimensions. And so I think, sorry, this is a long-winded way of saying that you need all three components to basically have this like unified planet formation model. Was that?
Cool. Yeah, thanks. Anyone else? All right, let's give
Yeah,
her another hand.
There's,
Oh, sorry, there's another one.
So, all the like observed compound elements, like those substances, are they reported from observations in our galaxy?
yes.
Right. So like we don't have yet some similar observations from some extragalactic source. Yes.
So it's very difficult, but I think last year we actually detected our first like exogalactic planet, like a planet in another galaxy. So I think we are getting into the realm where that could happen, but there's a lot of there's still a lot of difficulty in kind of like reducing that data, and we also have like so many mysteries within our own. Like I think that like it's very complex, because for the more complex molecules you can have a bunch more transitions that they can exist in. So it's very hard to disentangle whether the signal is actually noise, or because in terms of their spectra, they will be distributed across a larger wavelength. And so one of the biggest things is for like complex molecules, it's like, okay, is it noise or is it actually a signal? And so complex molecules are very difficult to already detect because they can exist in so many different transitions. So I think right now we're kind of limited in our understanding. But yeah, there was a cool paper that showed our first planet outside of our galaxy, which is really cool.
I have another question.
Yeah.
So, for instance, like astrophysicists trying to study some interstellar gas stuff, there are some circumstances that our assumptions on fluid dynamics breaks down, so we cannot use that theory. So I wonder if like there's a similar case, like some environment is so different from our usual lab that the chemistry we had breaks down in space. So I wonder like there's some cases like that, or if there was, like what kind of effort people try to overcome that.
Yeah, fluids is one of my favorite things. So in terms of modeling, I think the coolest, I think if I wasn't in astronomy, I would go into aerodynamic stuff like fluids, because I have a little bit of background in that. And I think the biggest thing is like we have like assumptions that make our physics really easy, like laminar flow or things like that. But I think what we really struggle with is modeling turbulence and eddies and all of that, because that can play a huge role in what reactions can occur. So in terms of, it's not going to always be smooth. Like I think turbulence is what creates the most complexity, and we have a lot of research left to do in terms of turbulence. I think that's a really cool topic that once we do get more understanding about what turbulence is, and because there's so many different ways it can exist, and like what eddies can form in atmospheres or in the disks, like all of those dynamics, I think, and like pressure differentials that result from that will dictate what chemistry can occur. So there's a lot of complicated axes. So I think we kind of, our models make it really easy to like cut down on computing time and stuff like that. But I think it's obvious that we have a really limited understanding of like fluid dynamics in terms of, I think turbulence and things like that would be the most, once we figure it out, it could help us a lot more in terms of reactions. Yeah, and we can see that kind of in our scales too, like in Chem E, like we kind of, it's kind of different than chemistry, because chemistry is like how does the reaction occur, but in chemistry it's like, in Chem E it's like how, when you scale that up, does mass and heat transfer play, or fluid dynamics, how those affect it. So you're not always going to have like this well mixed environment where the distribution is equal, and so all these different physical processes will affect what reactions can occur. So I think we see that even in our earthbound cases like reactors, we still can't model it really well there. So it's something that we have a lot of work to do to understand.
Thanks. Any others?
Thank you.